Hello everyone. In this video, we are going to cover the topic of autocorrelation, which is the last step when we are dealing with dynamic linear models. We want to check our specification in that model to be correct in terms of uh, respecting the assumption of linear regression, which is mainly the IID errors that are coming from normal distribution with mean zero and constant variance. And if our test on autocorrelation tells us that we're fine, then we can trust our inference. Otherwise, we should be really cautious, and uh, it's not wise to interpret that model and then make any inference based on it. So, just like the topic of heteroscedasticity in linear regression when dealing with cross-sectional data, that we end up to have non-constant variance and we are violating that this assumption. Similar to that, we are violating the variance assumption here in terms of we want to have the error terms to be completely independent. So if that means that error term at time t and error term at time s, and for any time t and s, it should be as well as they're not equal. It should be equal to zero. So if we find significant non-zero covariance terms for any values of t and s, then we are violating this assumption. So in a nutshell, that's what we want to do with autocorrelation. If you have that non-zero covariance terms, there is a case of autocorrelation. If you don't have it, everything's fine and okay. So we need to test to see whether we have case of autocorrelation or not. In econometrics, serial correlation, also known as autocorrelation, is a property of the model error. That means, as we talked about, we are saying that the covariance term between error term at time t and error term at time t minus 1, which is this, in this case, this is exhibiting the first order serial correlation, is non-zero. We can show that if there was a regression formula, we have ET the left hand side and ET minus 1 right hand side. If we get significant results for rho, then we have some type of correlation between ET minus 1 and ET. So as but on the other hand, if we can't reject the hypothesis that rho is equal to 0, then we cannot reject the no autocorrelation as the null hypothesis, and we basically fail to reject no autocorrelation, and we are fine. But if we reject the no autocorrelation, that means there is evidence for autocorrelation. So just as a reminder, if you from the previous session, we had this aggregate macro example. Let's quickly run it to the end. We talked about that generative specific approach and use use AIC, VIC, and ANOVA testing, the concept of grandeur causality, to come up with a good specification. At the end, this was model 4 ended up to be our best model, and we said there is a final step, which is checking for serial correlation or autocorrelation, which in the notes was like soon be discussed, and this is where we want to do that. We briefly did this at the end of the previous video. Let's look at the results again. This BG test is the function from the LM test package that runs our autocorrelation test. We will explain more in detail what is actually BG, what BG is actually talking about, and what is Broch-Gottfried test. So here we get a high p-value, fail to reject the null hypothesis, no autocorrelation. So that's where we stop and like, okay, we are fine with the model that we created. Similar to the autocorrelation of first order, we can have second order serial correlation. That is, not only there is a non-zero covariance between the error term at this time and time before that, but also error at time t and error at time t minus 2, two lags, two points in time before that is also non-zero. The equation is similar to the first order. We just have the second lag term added to the model as well. Similarly, we can define a pth order serial correlation and check for that. As you see, it's very similar to case of heteroscedasticity that we were creating another auxiliary regression to and estimating parameters in that to end up with our inference about heteroscedasticity. This is the same thing. Our analysis about autocorrelation is on the error term. That's why we are saying that autocorrelation in econometrics is property of the model error. You can have variables, time series variables that are having autocorrelation too, but just in terms of terminology, this is a common thing in this domain that if you just say autocorrelation, intrinsically you mean autocorrelation of the model error. So if you are talking about the autocorrelation of a time series variable that is not only residual in a sense, then you need to be more specific about it and make sure to mention the name of the variable as like, autocorrelation of this variable. That's something that wanted to point out here to make sure that we understand the difference. So what happens if our error terms are correlated? Well, similar to case of heteroscedasticity that we were violating that constant variance, here we're going to have wrong and invalid standard errors, and those standard errors going to mess up our inference. The estimates are still going to be unbiased and consistent, just like the case of heteroscedasticity, but their significance is not going to be trusted. So they are not best linear unbiased estimator anymore because of their biased standard deviation or standard error. Where in all this assumption, the variance of beta is just coming from some estimate of the sigma squared in our data. That is there is no covariance term, and covariance term are zero. In the case of having autocorrelation, then this would be invalid because we will have covariance terms that are non-zero, and this is completely not assuming that. So if you just move on and fail to check for autocorrelation and our model has that autocorrelation, we cannot trust our R square, we cannot trust the T statistic, the F statistic, and unfortunately our analysis is not going to have robustness. So what do we need to do to detect serial correlation? What we do is a combination of running a test and also visual inspection. We never give up visual inspection because sometimes you might have low number of observations, and these tests are usually not having enough power, and number of observations is low, so it's good to have visual inspection to bring in different kind of evidence for our analysis. So let's look at this example that we have. We had M4 was our best model. Let's change the parameters for the output of plots to having just one plot per pane, and now I want to plot M4 residuals, and I'm also looking use the type L line so it's time series so we can connect them, why not? And here it is. This is looking very stationary, kind of around zero, bounded, so it's a constant variance kind of case when mean around zero. One thing that could be tricky with this first order serial correlation example, as rho increases, this serial correlation becomes more significant. But what if it approaches to -1? So if it gets to -1, it is still going to be significant case, but visually it might not be as obvious as it should be because it's going to zigzag around zero. So that's why we need to also use a combination of stuff. Our test, we're going to show if there is some negative correlation when we run that BG test. So combination of the visual and BG test is going to help each other out. If number of observation is low, then visual inspection coming in help us out. If we have something funky going on, like a row equal -1, and it's hard to visually inspect it, that's where the test coming in and help us out. So in all these scenarios, we're trying to use various tools and methods to do our best. So what's the test is actually based on? The test is based on this auxiliary regression that we talked about. So if you're working with first order uh, autocorrelation, that's just only using one lag in this right hand side. Second order autocorrelation or serial correlation, we have two terms. Similar for the pth order. There's this test called Durbin-Watson test, and to some extent, unfortunately, it's pretty common to be used out there, but this statistic is only considering the first order correlation. So if you have covariance terms that are non-zero in other orders, and then you have a very close to 0, 1 for the first order, you're gonna say you don't have a case of autocorrelation because you haven't checked for the higher orders. So it's not going to be really helpful in practice because a lot of times the correlation is coming from an order older than one lag. So what we're going to do, we're going to use families like what we did with heteroskedasticity, like Bruce-Pagan test and heteroskedasticity. Here we are using Bruce-Godfrey. This time Bruce teamed up with Godfrey rather than Pagan. But they are all coming from Lagrange multiplier tests that you calculated calculate the LM, and then that LM is going to have a chi-squared distribution. In the case of uh, in the case of um, heteroskedasticity, the way that we were creating our auxiliary regression was a bit different than what we are doing here, but at the end, our statistic was a chi-square there too. In this case, in heteroskedasticity, we are using the square root of the residuals for our left-hand side, our dependent variable, but in the auxiliary regression, our residual itself going to be the left-hand side, just like what you see in this equation. So that's our left-hand side. And the right-hand side with the lags of the residuals, as many as we have defined by the pth order. So at the end, the R squared of the auxiliary regression multiplied by the number of observation minus the number of orders that we use for that serial correlation test would give us a chi-squared variable with p degrees of freedom. We take that variable to that distribution, that value to that distribution, and then see what probability value we get according to that. And if it was less than our um, significance levels, then we reject the null hypothesis. That is, we have autocorrelation. If it was above our significance level, then we fail to reject the null hypothesis. That is, we fail to reject no autocorrelation, so we are fine. As you remember, we had in the heteroskedasticity case, we had this HCCM estimator, which was the White method by White to correct for on those biased standard errors and then give you robust standard errors. Similar to that, we have corrections for autocorrelation, but we have this message from Graham Mason that uh, he says that in an article in Journal of Econometrics back in '95, he says a simple message for autocorrelation correctors: don't. Similar to what we said in heteroskedasticity, we don't suggest that. We want to use the information that we have in our data as the best we could in order to avoid problems with heteroscedasticity, similar to that, we're going to do the same thing with autocorrelation. Usually the main reason that autocorrelation is happening is that we haven't included enough lags in our model, specifically enough lags of our dependent variable. That is why there are some autocorrelation in our error terms, because that those stuff haven't been captured. So if we bring that information in, then the error is not compensating for that, thus end up to matching our assumptions for the OLS way better than in the case of auto correlation. So almost always you should include at least one lag of your independent variable if when you're doing I'm sorry, one lag of your dependent variable when you're doing time series analysis. It's really hard to assume that you know you're not going to bring any information from previous point in time of your dependent variable. If we use a general to specific modeling strategy, which we did last time in the dynamic econometrics models case, we're gonna be fine because we start from including basically everything that we have, the general pool that we have, and start like uh, getting rid of stuff on the right hand side that are not necessary to be in the model based on the test that we are doing. So all the necessary stuff that needs to be captured based on important information are there since we included them. We included everything and got rid of stuff that were garbage. So whatever is there, it's it's important. That way there is nothing out there for the error term to start, explaining, and errors start to not have any pattern. Thus, it's gonna have, constant variance, non zero covariances, and zero mean. So what we do the general to specific approach. At the end, we of the steps, we can do the serial correlation um, checking to see whether our final specification is right and we didn't do anything wrong. Just like the case of heteroscedasticity that we introduced the HCCM matrix, heteroscedasticity covariance consistent matrix. Here we have this HAC estimators that are they're going to be consistent for autocorrelation, and they in the case of heteroscedasticity, White has ended up to create that estimators. Thus, it was called White estimator. But here we are using the method by New Invest to develop HAC, which is both for heteroscedasticity and autocorrelation correction, HAC. But again, this is nothing that I personally suggest. I showed you how it's done, but in my opinion, we need to include more lags in order to solve this problem. So let's look at an example here. We're going to work with aggregate macro example 2. I'm going to close the first one. Let's clean up this stuff. So if, last time we did the general to specific approach, so we were fine. Now, in order to show how things could be wrong, we need to do wrong things first. So in this case, we're not going to go from general to specific approach. We're going to start from some specific approach, find ourselves in problem and trouble, and then start solving those. But the chance of that happening is way lower if we start the general to specific approach. The data set we want to work with is coming from days from the years 1950 to 2000. It's mainly quarterly data, so the frequency is like quarter based, and from first quarter of 1950 to fourth quarter of 2000. So it has about 10 years, 12 variables, and I'm sorry, it has 12 variables and about 50 years of data. We're not going to use all the variables in it, but here is the definition of the variables used in this data set. This is the source of the data set, but Actually, there's this package named AER, so if you haven't installed it, please install it. We use that package. AER is applied econometrics in R, and it has nice data sets in it. So here we are using the US macro G dataset from that package. This data function in R does that, goes get data for us, and that loads the US macro G package here for us, as you see, and now it's in the memory. I can use as data frame function to create my DF, and here I have, let's do the wrong thing. So first thing is time series analysis, stationarity. We need to make sure that everything is stationary. So we didn't do that. So we're doing something wrong. M1, I got a model of significant results, and someone might give up and then be happy about just this great model with significant all the stars there. But it's wrong because it's not stationary, it's non-stationary. Let's look at it. This is intward for consumption, non-stationary. This is intward for disposable personal income, non-stationary. So let's create these variables in cons and DPI, and then I take the difference of them because I want to fix it for non-stationarity and make them stationary. And now that they are difference, let's intward them, intward decons. I see that now this turns into a stationary variable, similar to that intward DPI, stationary as well. Now, I want to use that embed function to use create the lags of my variable and create some lags. Now, again, another mistake that we want to intentionally make to see how it works. We are only using the current values, so nothing from previous terms. So nothing from the lags. So we are using a stationary data. We are doing one thing less non-accurate or wrong, but let's look at the BG test. So Bruce-Scott-Free test, it's gives us a very, very small p-value. That is telling us that there is high serial correlation among our error terms, and it's perhaps because we didn't, include enough lags. Now I'm adding two lags of the dependent variables and two lags of the independent variable as well as its current one. So now we BG test that one. The p-value got larger, but still pretty small. So we still have the case of autocorrelation. Look at the summary of the model. I get some significant results, but I have autocorrelation. I cannot really do, make inference. But someone might come and say, hey, I ordered some lags. This is the model that I justify based on, um, other research done, stuff like that. But I have case of autocorrelation, and my solution for this is use HAC estimator. So similar to the case of heteroscedasticity in R, use library sandwich. Instead of using the white specification here, we use the new West specification for model 2, and then CoF test gives us the result for the t-test part. So if I compare these, the estimates here are equal, but the standard errors are larger in, are larger in this case compared to this case. Forget about the intercept one because the important thing is just the coefficients. We can see that all these standard errors for these coefficients are larger after that correction, which makes sense. That's the goal of the correction. The Wald test does the F test analysis for us, but still it tells us that now these are significant, and then go make your inference based on these guys. This is now 70% p-value, was 60%. This is almost 10%, and now it's 19%. So as expected, the some variables lost their significance. But what we want to do, we want to include more lags because that's the reason of having that problem in the first place, the autocorrelation problem in our error terms. So what I'm going to do is I'm going to include one lag of the consumption. So consumption today, and then one lag of consumption, the difference in consumption or rate of consumption from previous point in time, previous quarter. And for DPI, I use 1, 2, 3. So instead of spelling it out like this, to have LDPI1, LDPI2, LDPI3, we can say just column 1, 2, 3. Run that, we get the summary of it, and pretty much every term is significant there, and then run the BG test, and we have low p-value. It's not lower than 5%, but it's close enough to that to kind of consider the serial or serial correlation. So let's add more lags. So now I'm adding another lag from consumption. So not only column 2, column 3 is coming in, and then run the summary. Also, some significant variables there, and then BG test for that. Again, I have low p-value. So now let's add one more lag. And now here I have up to column 4. I'm also including DPI up to column 4. Here's a summary of it. And usually the decons, even the final one that I added is pretty significant. That shows why it was important to add that. We were missing that information. But while you're using this and you stop there, you're not bringing that information in at all. So why not utilizing what you have? That's the whole point of analysis. You always want to bring more data in rather than throw valuable data out. So let's BG test that one. 35%, high p-value, fail to reject the null autocorrelation null hypothesis. The second order, the third order, all of them high p-values. So we can, feel confident about this model and then say that we fixed the autocorrelation part. Looking at the summary of it, I see that the final lags of my DPI are not that significant, so I can drop them. Don't use up to column 4 and use up to column 2. And now I can run that model and get the summary of it. And we can see that here now I have all those significant variables only included. I also included anything before the significant lags. Here too, I didn't drop the non-significant ones. As we talk about the DLM section is very important. So let's look at the AIC, VIC. This is not necessary anymore. Used to be necessary for running BIC. And in AIC, we can see that AIC of model 6 is smaller. BIC's model 6 is smaller too. So model 6 is what we want to go with. And this is this was just like to show an example of what we're dealing with when we face a case of autocorrelation. However, if we had started from general to specific approach, we would have started from something like maybe max number of lags equal 4, maybe something like this, 2 to 4, and then 1 to 4. End up to see, oh, we don't have any autocorrelation. We just have some extra stuff that included here with no significant t-test at the final two um, embeddings of this vector. So we drop them, and at the end we BG test whatever the result was. We see still we have high p-values, so we are fine. And as you see, if we were doing general to specific approach, this from here to here would have been done with our problem. But because we didn't do the right thing and we started with a very specific approach and started to generalizing a step by step, then that's gonna take more time, and then it's, we also might not be lucky enough to get to the right answer because we're creating more complexities. Well, this is it as a end of the topic of autocorrelation, and thanks a lot for watching.